Hello everyone, welcome back to Alkaline Hydroxide 784, and today in the chemistry series we'll be looking at carboxylic acids and derivatives. Okay, so what this is referring to is carboxylic acid, acyl chlorides, and esters. So yeah, let's just go into the learning outcomes. So the first one is to describe the formation of carboxylic acids from alcohols, aldehydes, and nitriles. So to form a carboxylic acid, you basically just oxidize other things. So if you oxidize an alcohol or you oxidize an aldehyde, you'll get a carboxylic acid, which I think we're already very familiar with that, so you don't really have to look too deep into it. Just use your KMNO4 or yeah, I think KMNO4 is enough. You don't need to because K2Cr2O7 is for when you want to make a ketone, and if you just keep continuing to react it, you'll eventually get an acid. As for nitrile, it's a little bit different because a nitrile has a C triple bond N kind of group, and usually what you do is you react it with something like HCl or something like that to first make it into the acyl chloride or something like that, and then make it into a carboxylic acid. So the reactions for that I will be writing down below, and the conditions as well if there's any particular condition, because this can be done either using acid. If you use HCl, you will get a acyl chloride, or if you use sodium hydroxide, you will get a salt with Na plus ion, and from there maybe you can change it into an alcohol, or you can acid, or you can change it into acyl chloride. Okay, so the next thing that we need to do is to look at the reactions of carboxylic acids and the formation of a bunch of different things. So the first thing you can do with a carboxylic acid is to make it into a salt, and the easiest way to do that is to react it with a base, because yeah, just react it with a base or something that will provide the anion to make the salt. Yeah, so not anion, the cation. Because the carboxylic acid will break, like when you dissociate it in water, you have the H plus group, and you have the rest of it with the negative charge to it on the O. And if you put a base, for example NaOH, you have Na plus and you have OH minus. So the OH minus and the H plus can just become water or just hang around, and the Na plus and the the ion that you get from the acid, basically the conjugate base in the sense, can then react to become a salt. And that's what I was talking about earlier. When you hydrolyze a nitrile with NaOH, you will get the same thing in a sense, yeah. So that's how you make a salt. So next one is to make esters. So esters are I think people are pretty familiar with them usually because they cover these things earlier than a lot of other things. So esters are things that you can make by reacting alcohol with acid, and it's a condensation reaction where water is released. And yeah, I think it's pretty simple. If there's any conditions, I'll just write it down. So the acid and the alcohol react to produce water and the ester. And the way of naming the ester is like, if you're a bit confused as to how to name the ester, you first have to look at the usual naming of an ester. So if you use this example ethyl ethanoate, which is not a good example because they both use ethyl like ethane kind of thing. But the like for the alcohol you would have yeah, you have like a different way of saying it, and for acid you have a different way of saying it. So when you say an acid, you would say something oic acid, right? So an O8 would be actually the acids, in the ester form. And that's how you figure out which order to name the thing. and that means you would have to first write the write the thing for the alcohol side, which is which ends in the YL, the aisle, ethyl, then write the one that's for the acid, which ends in OH. Yeah, so that's how you figure it out. Okay, so for the third reaction, we look at how you make acyl chlorides, and this is pretty simple stuff, I guess. Just use the same stuff that we used last time, in making and replacing an OH group with a Cl group. Only this time it might actually be easier to do, just because we are dealing with something that's slightly more reactive. So instead of alcohol, we deal with acid, and we can use like PCl3 or PCl5 or SOCl2. So yeah, that's for chlorides, and it'll happen pretty quickly, and it has the same effects as to what products you'll get. So SOCl2 will give you the all gaseous products which can be separated from the product that you want. Okay, so the last one is making primary alcohols, which would require to reduce the carboxylic acid, and you can do that with lithium aluminium hydride, LiAlH4. And yeah, that's pretty much it. Just use that, and I believe you use a ether, lithium LiAlH4 in ether. So you can then do your primary alcohol, reduce it to that using our reduction catalyst. Okay. So the next learning outcome is to explain the acidity of carboxylic acids and of chlorine substituted ethanoic acids in terms of their structures. So basically carboxylic acids are acidic because they're literally called an acid, but that's not the reason you should be using. The reason is because when you have this nice little OH group, and you also have a double bond O. So a double bond O makes the carbon even more delta positive, and therefore it drags the electrons from the it doesn't drag the electrons from the OH, does it? Okay, never mind. So the thing is, it's actually gonna be dragging the negative charge from the OH group, and even when the H leaves it, it is going to be quite stable. It won't want to bring the H back to it as quickly as compared to an alcohol or something else. I mean, of course, compared to an actual strong acid like HCl, this is still not as strong, but you get the idea. So it's going to be a little bit more stable in a sense. And if you use chlorine in your chlorine substituted ethanoic acids, what does that mean? Does it mean acyl chloride, or is it just ethanoic acid with a random chlorine group? Wait, what? Okay, anyways. Yeah. Now if you have a acyl chloride as in terms of acidity, it will be quite reactive. It will definitely want to become an acid immediately because of the Cl group. So in this time, instead of the OH, being the thing that has to be stable, we go straight to the C plus ion there, the carbocat ion kind of thing there. And wait, actually that ends up making a positive charge. Okay, actually I don't know what I'm saying. Okay. Anyways, the Cl just likes to react with everything, and then it becomes a normal, like the same scenario as the acid, so it just reacts faster. So the reason is because the Cl likes to be replaced, so it makes the carbocat ion really positive in a sense. And of course you might be saying that the OH group does that too. Yes, you're right. But in this scenario, we're looking at this on its own with regards to why it likes to substitute so well. And also, in a way, the Cl has, more free electron pairs, and also, like, the bond between the C and Cl is slightly weaker than that between C and O. So there's a lot of factors that go into it being quite reactive in a sense. So yeah, it just becomes the same conjugate base eventually by reacting with the water instead of dissolving in it. Okay, so the next one is to describe the hydrolysis of acyl chloride. So this is basically the reaction that happens. So the Cl group will leave the acyl chloride, and it will then be replaced with a OH usually, because if you put it in water, that's what's going to happen. Or if you put it in something that has a OH group, that's what happens. If there's some other nucleophile, you will get a different nucleophile. So nucleophile will easily attack the carbocation because it is so positive right now. And yeah, the Cl group will then leave and be replaced with a new nucleophile. That's the hydrolysis of acyl chloride. Yeah, you can use hydrolysis as in with water, that's what happens. OH minus will be brought into the equation. Okay, so the next one is to describe the condensation reactions of acyl chlorides with alcohols, phenols, and primary amines. So earlier we saw how esters form. So let's think of it in the same way, only thing the stuff you get may be slightly different. Okay, so if you react an acyl chloride with an alcohol, you will then get a condensation of not water but HCl. So you still get an ester, it's just that you don't get water in it with it, you get hydrochloric acid instead. So yeah, that's kind of scary. Yeah, then with phenols you will then get with phenols you then get the same thing with like a phenol instead, and with a primary amine you would then get like instead of an ester per se, you get something. What's the thing called? It's like the like how we have the 2,4-D DNT pet, the deep. Okay, I don't remember the name of that. Oops. But you get what I'm talking. 2,4-DNPH. Yes, it looks a bit like that, I guess. If you know what I mean. I'll just write it down, and you can figure this out. Okay. So yeah, okay, that's cool. So the next one is to form. The thing is, when you are doing this, right, the esters, whether you can form an ester or not, is dependent on what you're reacting the phenol with. So actually acyl chlorides will form esters with phenols, but phenols won't form an ester with a carboxylic acid. That's the crazy part of it. That's how reactive acyl chlorides are. That's why you can actually do that pretty easily. So next one is to explain the relative ease of hydrolysis of acyl chlorides, alkyl chlorides, and aryl chlorides. No matter whatever it is, the fact that the chlorine is there makes it reactive. That's pretty much the logic here. So chlorine makes the carbon pretty positive, and it doesn't even have like a random hydrogen tagging along with it to reduce its impact. It is completely just the chlorine itself. And that's the reason why the double bonded O is stronger than the OH group. And in a way it makes sense given that both the O's bonds are like dragging the electrons away from the carbon. So likewise for the Cl, since it only has one bond to make, it's not going to make it with a hydrogen. We kind of just, all this attention is on the carbon. But please don't write your answers like this. That's a very weird way to describe that, but you get the idea. Yeah, so since chlorine is very reactive, it likes to react with many things. It has many, extra electron pairs, and it is somewhat electronegative. Even though it's not as electronegative, oxygen is still more reactive than a hydroxide group somehow. And yeah, okay, so this makes all these chlorides quite reactive, and they're very happy to be replaced with water. So basically the Cl isn't something that likes to stay there for a long time. It just likes to leave. In a sense, it likes to leave. And actually if you remember that in the phenol substituted groups, right, the OH group is actually an activating group when it comes to a benzene ring. Of course, it's not related to this particular explanation. I'm just gonna quickly tangent off, and the Cl group is deactivating. So what happens here is actually the the OH group is likely to become less negative on its own, but the Cl group isn't going to do that. It is going to pull out all the electrons away from the carbon no matter what. So there is that greater likelihood of Cl making it more, unstable, making the bond more unstable and more reactive in the sense. Reactive as in because it's very positive and very attractive to nucleophiles. Okay, anyway, so the next learning outcome is to describe the formation of esters from the condensation reaction of acyl chlorides using phenyl benzoate as an example. Okay, so I already just mentioned that phenols work with acyl chlorides, but they do not work with acid like carboxylic acid. So yeah, there's nothing much to really say here except for the fact that it just happens. Okay, so yeah, I can just write down the reaction and that's pretty much it. Okay, so the last one is to describe the acid and base hydrolysis of esters. Right, so esters are esters and they are formed from condensation. So the opposite to that is if you want to bring in a water molecule and then break it up. So that's why it's hydrolysis. So you can do this either with acids or with bases. So I will write down the two equations for that right now. And under various circumstances, you can like break the ester up using an acidic method or a basic method. And I think there's a few steps to each of them. So let me just write down the conditions for that. Okay, so yeah, that's all the learning outcomes for today. If you found this video useful, you can press the like button and subscribe. And before I sign off, I'd like to say that there's maybe 1, 2, and there's like 3 more episodes left in this series, and plus another episode related, maybe another episode or 2 related to the exam per se. So yeah, that's just updating you all on that. This is episode 18, by the way. So yeah. Okay, so with that, I would like to say thank you and bye.